But yes, are we good, John?
Yes.
Okay, so J.J. Thomson's model of the atom, we're back in 1904, and Rutherford has discovered alpha particles, beta particles, and so what Rutherford sets out to do is, being a good student of J.J. Thomson's, he wants to prove that J.J.'s model is right. And so his idea is, discovered these alpha particles, these big, grunty helium nuclei, just a concentrated ball of positive charge. What would happen if we fire a beam of alpha particles into this atom, into this atom here, and use that beam of particles to kind of probe into the atom and test what JJ has theorized about the inside of the atom. So that's what Rutherford did. He set up this experiment where he had a beam of alpha particles that were headed at a sample of material, and for his material he chose gold. The reason he chose gold is you can hammer it out really thin, so it can be just like a few hundred atoms thick, and hopefully by doing that he might get some alpha particles that just interact with only 1-2 atoms and actually see the effect of an alpha particle passing through a single atom. And what effect might we expect to see if we have an alpha passing, like, let's have a look at a few different cases. We have an alpha there going just past the atom, or an alpha going through the middle, or an alpha maybe going through the side. What would each of those do we think? No.
Yeah, like attracted to the electrons.
Attracted. Hang on. Let's have a think. The alpha has got a 4-2, which means that we've got 2 protons and 2 neutrons, and inside this atom we've got a whole lot of except that. Let's cancel that. We don't have protons and neutrons back in 1904, right? Just cancel that. We got these alpha particles that are big balls of positive charge and mass, and we've discovered the electron, and we've managed to work out that it takes about 2,000 electrons to make up the mass of one, or that the electron is much less massive than the alpha particle. And so driving an alpha particle into an electron is like driving a bus into a mosquito. Or like driving a bus past a mosquito and the bus getting attracted to the mosquito. If they've both got the same pull on each other. So we can kind of discount the electrons from this because they've got such little mass. And so now, rethinking about it, what might we expect to happen if we've got this alpha and this evenly spread, positively charged mass?
Move away from the...
Move away, right? So this alpha up here, what might happen to that one as it passes close to the atom? What we might expect to see is a little deflection.
But why is it going away?
Because we've got a positively charged matter inside the atom and a positively charged alpha particle.
So the negative charge of the electrons is just negligible.
The electrons, because they're negatively charged, they will undoubtedly feel the attractive force of the alpha particle as it races past at 10% the speed of light, and that will rip them out of the atom, causing the atom to be ionized. Remember, we know that alphas are highly ionizing, so as this alpha zooms past, it will definitely rip electrons out of the atom.
That makes the
ionizing
why does it
them.
still go away though?
But it's like the mass of a mosquito compared to the mass of a bus. They're not going to, they might get pulled out by the bus as it goes past, but they're not going to make the bus change its path at all, because they've got so little mass.
So therefore only the positive matter makes the bus move.
But because a gold
on the other bus
atom has much more mass, like if we look at gold on the periodic table, it's up at something like 100, the nucleon number 196, and we know that the alpha particle, by this stage we'd worked out that an alpha particle kind of turned into helium. We've fired alpha particles into little glass vials, and noticed that if we fire alphas into little glass vials, we end up with helium gas. And so we kind of worked out that alpha is helium. And so we know we've got one that's got a kind of a mass of 4 and one that's got a mass of 196, and so much more massive. And so we're happy that it's going to be deflected. Two positives repel each other.
Yeah, that makes sense.
And we ignore the electrons because they've got such little mass. What about one that goes through the middle?
It's going to bounce off.
Bounce off.
Yeah.
Hit,
Affected
yeah,
at right
hit
angles,
the,
go
hit
that
the
way.
sides.
It squishes together.
Except it's going at 10% the speed of light. So JJ's sort of hypothesis was, well, it's going to just go kind of ploughing on through, and one that goes through the bottom, we might see a little bit of deflection, kind of like that. And so what Rutherford was hypothesizing from JJ's model is that we're going to see a little bit of deflection. He did some quite complicated calculations and worked out kind of what spread of alpha particles we might expect to see after they've passed through the gold foil, and then designed this experimental setup. He had like a screen that wrapped right around the over here, and on the screen it had zinc sulfide coating. Zinc sulfide is that thing that glows green when stuff hits it. And so the actual experiment, they did it in a dark room. He had these two students working for him, Geiger and Marsden, and they had to sit in the dark room and like count green flashes. Every time they saw a green flash, they'd like record where on a grid it happened and use that grid to kind of work out how much the alpha particles were deflected by. Probably the reason why Rutherford's on our $100 note is because he didn't just put the screen in front of the experiment. He did the ridiculous thing of wrapping that screen right around the back of the experiment too. Put the screen where there would be no alpha particles, which meant that he saw there were lots and lots and lots and lots and lots of little green flashes straight ahead. Most of the alpha particles went straight through. There were a few that got deflected by like a small angle. Not quite what he predicted. He expected more of a spread. And then completely unpredicted, occasionally, there was some over here behind the experiment. And that's just like, there's nothing in JJ's model that can help explain why there would be just occasionally an alpha particle that is turning up behind the experiment, like it's bounced off the atom. That's like a completely unexpected result. And so Rutherford has to come up with another new model for the atom to explain how come every now and then there's one alpha particle that seems to bounce off and be seen behind the experiment. And so his theory, his way of explaining this was to get rid of JJ's model, put his own one, Rutherford's model. He concentrated all of that positive charge into the center of the atom, and really, really, really small, at like a fraction the size of the atom, all of the positive charge and all of the mass crammed into one little space, and the electrons were, according to Rutherford, doing loop-the-loop around the nucleus. And so his negative electrons were not at fixed points. They were in orbit around the nucleus, held in place by the electrostatic attraction. And the evenly spread positively charged mass was now concentrated into a tiny volume called
Nucleus.
right. And so the way Rutherford's model can explain these results is that the atom is mostly empty space. So the vast majority of the alpha particles pass through the atom without any influence at all from the positive charge because they're so far away from it, nor from the electrons because the electrons have such little mass. The few that are deflected by a small angle, they're ones that have kind of passed close to the nucleus and they've felt that electrostatic repulsion, and it's been enough just to cause them to be deflected from their path. And then the way that we can explain these crazy flashes that are happening behind it, these are from alpha particles that are on a collision course with the nucleus, and something like 1 in 8,000 alpha particles deflect off, which means that 1 in 8,000 actually, according to Rutherford, were on a direct collision course with the nucleus, and they've actually bounced off and been reflected back over here. He famously said that this result was kind of, was like firing a gun, like on a ship, like a navy ship, at a piece of tissue paper, and having the cannonball bounce off the tissue paper, come back and like, hit you. That's how improbable it was. That's how he felt about finding this result of an alpha particle that was behind where it should be. So it's because of finding this that Rutherford decided there had to be a nucleus, and because of that made it onto the $100 bill for discovering the nucleus of the atom. Obviously we have to improve a little bit on this model. It's not quite what we learn in science yet, but it's suddenly looking a lot closer.
Just really lucky.